All right, today's lesson is on section 5.4 in your Pre-Calculus 12 text by McGraw-Hill Ryerson. We are on page 266 is where we're starting. What we're talking about today is equations and graphs of trig functions. We have talked about solving trigonometric equations, right? We are going to basically continue that with some trig functions, and we're going to use the calculator, okay, the graphing technology. We're going to use that to solve a little bit, so we're going to get some practice with that. And yeah, just maybe do a few more word problems, kind of real-life applications. So on that note, if you look on this page here in your textbook, it says that one of the most useful characteristics of trig functions is their periodicity. This word is pronounced periodicity. And what it means, it's the characteristic of the functions to be periodic or repeating in nature. So if you look at this diagram on the right, this is sort of why sinusoidal functions in particular are very helpful for describing a lot of natural situations. Here is a tree in spring. Here's the tree in summer. Here's the same tree in the fall and in the winter. Now the next picture that would come after that fourth one of the winter would be the spring again. And summer, fall, winter. Spring, summer, fall, winter. Spring, summer, fall, winter. You kind of get the picture, right? It repeats. So when we're talking about characteristics and trying to quantify things that happen in a periodic, repeated sort of fashion, the sine and cosine graphs are going to be very, very helpful. Okay? So we will see that as we move through. That's periodicity. So some examples, times of sunsets. You know what? The sun sets every day, doesn't it? So that happens quite regularly, every day. Comet appearances. They're a little less frequent than sunsets, but still, we could graph, you know, this, and obviously the domain or the years or whatever might be quite a bit bigger than the sunrise or sunset, but you kind of see how the regular occurrence could be graphed in such a way. You know, seasonal temperatures, waves in the ocean, even the quality of music sound can be described by trig functions. Mathematics and scientists use the periodic nature of the trig functions to develop mathematical models to predict many natural phenomena. Okay, so we'll get to that in a bit. Here's an example here, and now this is not you know, a real-life problem related, but I just want to kind of go over a couple things. You have solved equations in the past, and we've done these trig equations, right? And we've always used the unit circle. I just want to remind you that we can solve graphically using the graphing calculator, or whatever graphing technology you want to use. So maybe I guess we'll have to pause for all of you to get a graphing calculator, and then let's just run through this, and we'll kind of do this example. Okay, so take a break, grab a graphing calculator. We'll be back in a sec. If you have your calculator and you have this screen clear here, what we're going to do is we're going to take a look at this equation right here, highlight that, and we're going to put the function that relates to this equation in the calculator. So notice that here, this one side would be one function, the other side would be the other function. So because this is 0, we're just going to plot y equals this, okay? And so you see that on the screen down here. So we're going to do this. A quick note: you're going to have to do some fancy footwork with the parentheses here for your graphing calculator, because we're using the TI-83. And you have to have an extra set of brackets to make the squared. If you put the squared inside there, it's going to think you just want the x squared. So we have to put it in just like this, okay? So we're going to go to bracket, so times, and then you're going to want to go cos of x, bracket, and then you're going to want to have another bracket with a squared there. So that means that we are squaring the entire of this cos function, and then minus 1. Okay, so that's how you put that in. And again, if this side is 0, you just need to put the 1 in, because what we're going to do is when we solve this equation, we're going to find the roots, right? So we're going to find the zeros, or the roots. So if you graph that, I have no idea how your window looks. I think this is a pretty standard window here, and you might have something like this, okay? Now, this down here in your text, that's quite a bit more helpful, because you can see these zeros a bit better. So let's adjust the window settings. We don't need so much y, and we don't need so much x here for sure. So why don't you take a minute to just adjust those window settings. Okay, so I adjusted the window settings a little bit with you here, and we want to see at least a couple periods here. I think I went from -1 to 7 up here, and then from -3 to +3 there. So we kind of have the graph here. We're looking for solutions, right, in the interval of 0 to 360. Now, the calculator is in radians, so that's fine. 360 we have to understand is about 6.28 radians, right? So if it's a cos graph, it looks like there's one period and there's two periods, okay? So 1, 2, 3, 4, 5, 6.28. So it looks like our period length, right? Looks like our period length is decreased a little bit here. Interesting, hey, with that squared. However, the bottom line is, when you graph this, it's going to be easier for you to know where your solutions should be. So from 0 to 360 degrees, we should have 1, 2, 3, 4 solutions. See that? And so what you want to do is, and this is a calculator tip that you should know already, second function trace, the calculate menu. Let's go to 0, number 2. Now, you're going to have to do this individually. So if you want to find the first 0, you're going to have to tell the calculator, okay, I want you to search between this left boundary and this right boundary. Just go on the other side of it. And see the arrows there. And then guess. And then it should tell you where this first 0 is. So it's at x of 0.7853. That's what it's saying. Now that's in radians, right? That's in radians. So the calculator, you know, looks like we're talking about degrees. So you're gonna have to convert that. If you want to show degrees, that's no problem. Change your calculator to degrees. But then you're gonna have to realize you're gonna have to change your x-axis to 0 to at least 360 or more. Okay? So I think I might just do that in case you want to do that. So mode, let's go to degrees, and then my window, your x max, instead of 8 radians, we need, you know, 380 degrees at least to see that. So it shouldn't change too much, other than you have 380 little tick marks here that, you know, make that look like that. Okay. So if we do, let's do the next one. Let's find this next intercept. It should be looks like 135 degrees, right? So let's do this. Let's go over here to the left of the intercept. Hit enter. Now we're going to go to the right side of the intercept. Hit enter, and then guess. It should guess right there. Oh, look at that. 135.0. Okay. So that's how you can use your calculator to quickly find that. Algebraically, you could solve this algebraically pretty easily as well for this particular one. Here's method 2, solving algebraically. And this is what you're used to doing, right, with the unit circle. So we solve for cos of x, and it says plus or minus 1/2. All right, when you take the square root of 1/2, you do plus or minus. So that simplifies to 1 over root 2, or root 2 over 2. So you're looking for all those angles in, you know, 0 to 360 that satisfy this for cosine. All right, and okay, so we're looking at 45. Okay, we're looking at 315. Now, why does 135 not count? Why does 135 not count? So algebraically, we found here that we're looking for a negative. But why on here? Why does this graph show us 135 as a root? Because we would look like there's 1, 2, 3, 4 roots, right? And is that true? Well, we've got 45 and 315. That's for positive. And for the negative version, we have these ones. So are there 4? There are. Okay. So you just kind of be careful with squareds and stuff. Graphing, you should never go wrong with graphing. But you may run into trouble here if you don't put the plus or minus. You may come up with just 2 answers. I don't know. So gotta be careful. So it looked like maybe we were off track, but it looks like actually that we're good. So everyone see that? Intercepts? All right. If we go to another example here, this one here, we've been over this before, but what you can do is 2 things, right? You can combine all of this into one function, let it equal 0, right? You can move the 16 over and let it all equal 0, find the roots of that corresponding function. Or the other thing that they show you here is that you can graph two functions. The first one is this on the right side, okay? That one, y equals that, which is this right here. And then you can graph y equals 16. Do you remember doing that? All right? You could do this as well. Now, it's easy to move that 16 over to just graph one function and find the zeros. However, if this was more complicated, you wouldn't maybe want to do all that combining, and you might want to just graph both of them. Like if they were both trig functions, right? Let's not combine them. Let's just graph one, or graph two of them. So here, we're finding the intersection points then. Okay? All right. Yeah. So points of intersection, here they are. That's the one graph, and here's the y equals 16. Any questions so far? All right. I do want to point out something that's kind of important here, but it's about general solutions. Okay? So this question asks for in this example 2 that we just looked at, determine the general solutions. Okay? And I want to just pause here for a second. If you look in your textbook, the general solutions are a little bit funny. Where does this 12 come from, right? So if we kind of go back to this right here, you might remember, just blue. Okay, let's use blue. You might remember that if we have a solution, something that looks like this right here, and we have this one right here, a general solution would have been like whatever this is. This was pi. Let's say this was pi over 3. The general solution would be pi over 3 plus 2 pi n. Right? That means every full rotation would have another corresponding root, right? So this plus 2 pi. And then you'd have this one. Let's say, this one is, whatever it is, like pi, whatever. So then you go pi plus 2 pi n, right? Because you're saying that this is a solution plus every full rotation, right? So what you have to consider, though, this right here, when you're doing your general solution, this is the period length. And 2 pi is the period length for a standard sine or cosine graph, right? That's the period length. But in your questions, and let's say we go back to this question, the original problem had a bit of a different period length, didn't it? See, this is the period length. This is b value, which will give us a different period length. So when you're doing general solutions like this, what you have to consider is the period length. So period length. So in this case, it would be 2 pi for a cos or a sine, 2 pi over, and what was it, pi over 6? So what's that? That's 2 pi times 6 over pi, which is 12. So that's where that comes from in the textbook. Right here, when it says the general solutions are, they find their answer graphically, whatever, and then they say plus 12n, where n is an integer. It could be positive or negative whole numbers, right? So you have to use the period length there. So that's just a note of caution. You have to make sure you do that right for general solutions, right? So you can name all the solutions that you get and just add whatever the period length is times n. Okay, do you have any questions right now? Because I'd like to take a look at just the one word problem here before we end. Okay, so let's just finish off with this word problem. It'd be we'll go through this one. Okay, so example 3 on page 271 in the textbook. The electricity coming from power plants into your house is alternating current. That's AC current. This means the direction of current flowing in a circuit is constantly switching back and forth. In Canada, the current makes 60 complete cycles each second. The voltage can be modeled as a function of time using the sine function. So again, when we talk about electricity, this current kind of back and forth, that's periodic in nature. So we can use a sinusoidal model. So here it is, V equals this right here, 170 sine 120 pi t. What is the period of the current in Canada? The period. So what would be that period length of one complete cycle there. What is the b value here? What's the b value? 120? Close. Remember, pi is just a number too. Yeah, it's not a variable. Pi is a number. So b is 120 pi. So the period length for a sine function is going to be, and there's the solution right there, but how do we get that? Well, the period length is going to be 2 pi over 120 pi. Right? Which is what? Pi's cancel out. That's 1 over 60. So the period length is 1 over 60 in this case. So that's how they get this, 160. Okay? So let's see, from 0 here, yeah, there's no phase shift, right? If we look at our equation there's no phase shift right here, and there's no vertical displacement. So it's going to be a sine graph, and one complete rotation there to there, that's going to be about 1/60th. Okay? So from there, from the beginning to the end of the one full rotation is going to be 1/60th. All right, so then it says graph the function. All right, so again, on your calculator, y equals, plug it all in there, and you should get something like this after you've adjusted your window. Okay, so why don't you take a moment to do that. Okay, so we got a graph like this. Just a reminder, when you type in a trig function like this, and especially when you have pi, and there's no indication that this must be in degrees, this x, it's going to assume it's radians. So you're going to have to make sure your calculator is in radians by default there. So we had a little trouble getting our graph there because we weren't in radians. So anyway, so here's where we have the graph. The amplitude is 170, so you got to have your y value pretty close to 200, negative 200. And this x right here is very, very short. 1/60th, right, is right here. All right, so if we graph that, what is the what are we looking for in this example? Let's just see. So explain what the scales on the axes represent. Okay, so we just talked about that, I guess. Suppose you want to switch on a heat lamp for an outdoor patio. If the heat lamp requires 110 volts to start up, determine the time required for the voltage to first reach 110 volts. Okay, so the voltage, that's the y value. So this is voltage here. Okay, that's what that axis means. And this is the time. So if we're looking for where 110 volts is and the time associated with that, that's going to be, I guess, back in this diagram. We're going to look for 110 here. Where is 110 and where does it first hit the graph? Where does this current actually get to 110 volts first? So that's what we're looking for. So when it asks this coded question like this, 110 volts, you're like, okay, where's volts? Oh, V, volts. Right, so that's in the Y position. So that's what my Y-axis is. Okay, that's the meaning of it. And when it first hits 110 volts, right, to first reach 110 volts, that's the first intercept after 0. So if we just take a moment to do that, this is what you should do. Y equals, go down to the next Y equals there and hit 100, say, so we graph that as well. You'll see this line jetting through there. So we want to find this intersection point right here. Right there. Oh, what did I put? 100? Thank you. 110. You're right. Let's try it again. Oh, it's going to graph the both. So there's going to be an intersection point right around here. Okay? So we want to find that, and of course, the intersection, second function calculate, 5, intersect. It's going to ask you for the first curve. Yes. Is this the second curve? Yes. And here's where it's important, really important, to move your cursor close, very close to the intersection point you want to find, because there's 1, 2, 3, 4 on the screen. So if you have your cursor over here, it'll find this one. If you have your cursor here, it'll find this one. So let's see. The cursor should show you where it is, and 0.001866 seconds. Okay, so they've rounded to 0.002. Anyways, so there you go. That's your time right there, 0.00. And you want to be as exact as you can, so you write that decimal down. That's where it would be. Okay. All right, so that's a that's a quick peek at what we're doing this lesson. Example 4, I'm not going to spend the time to go over it right now, but this is where you would plot, okay, you would, and have we done this in this class, right? No, yes, no? Because I just got finished doing this with the Foundation 30s for like a week, 2 weeks. Have you done this before where you plotted the points, found a curve of regression? You ever heard that before? No? Okay, okay. We teach a lot of math classes here. I can't remember what I taught you. Okay. That will be another video, okay, on this, another lesson, and I may do that today, I may not. But anyways, this question here, you can use your calculator to input values into lists in the calculator, and you can get the calculator to come up with a graph that would represent that data. And so here's a picture of it, you see. The calculator can actually generate a sinusoidal graph to model the data that you put into the calculator. So that'll be, I might show you that. I got a little bit of time here. But anyways, we won't do that here in this lesson. That'll be another quick lesson. So here's the key ideas here. Let's just take a minute to read through that while I get your assignment together. Okay, so here's a suggested assignment from 5.4. And I think number 16, you have to generate your 16. You have to generate your own equation, so you don't have to do that right now, but maybe coming in the future.